56 million years ago, Earth plunged into one of the most intense warming events in its history, the Paleocene-Eocene Thermal Maximum. Temperatures soared, oceans shifted, and life was forced to adapt in dramatic ways. Tonight we'll uncover how this ancient climate shock reshaped the planet. If you enjoy the journey, please like, subscribe and share, and tell us in the comments what surprised you most about this extreme chapter in Earth's past. Thank you for watching. Now let's begin. The early Cenozoic planet is already warm. Long after the end of the Great Cretaceous reptiles, the world settles into a greenhouse climate, a state in which large ice sheets are absent and average temperatures stay high across almost all latitudes. Oceans cover much of the surface, and sea levels stand higher than in many other intervals of Earth history, so shallow seas spread widely over low-lying continental margins. The air holds more water vapor clouds form readily in a thick, humid atmosphere, and storms move across the globe along broad belts steered by persistent winds. In this setting, the Paleocene unfolds as a time of relative climatic stability on geological scales, with no large ice caps at the poles and only modest temperature differences between the equator and high latitudes. The poles are cool rather than deeply frozen, and conditions are mild enough to allow forests and wetlands to reach into what will one day be polar regions. Warmth extends into the depths of the oceans as well, so deep waters are not as cold as in later Ice Age climates, and the contrast between surface and deep temperatures remains small. In the northern hemisphere, the early Atlantic Ocean is still narrower than it will become, and the continents stand closer together. North America lies farther south than in later times, and Greenland sits as a broad high land between the high latitudes and the North Atlantic. Europe and Western Asia are partly separated from the open ocean by shallow epicontinental seas. In the southern hemisphere, South America and Africa have already separated, but the gap between them is smaller than it will be, while Antarctica is still connected to other southern continents, or only beginning to open seaways that will later circle it with strong currents. Around the equator, wide stretches of warm ocean link the western part of what will become the Pacific Ocean with the Tethys region and the developing Indian Ocean, creating long, continuous pathways for heat and moisture. These oceanic connections allow warm surface waters to move efficiently around the planet, smoothing out temperature contrasts and helping to maintain a generally equable climate. The atmosphere above this arrangement of land and sea is rich in greenhouse gases compared with later ice ages, with levels of carbon dioxide high enough to keep outgoing heat from balancing incoming solar energy as quickly as it would in a cooler world. Under these conditions, the planet's energy budget reaches a stable balance at higher temperatures, and the climate system responds with gentle but persistent warmth, rather than sharp swings between cold and hot states. Seasonal cycles still shape regional climates, but winters at mid and high latitudes remain comparatively mild, and summers bring long periods of comfortable warmth rather than extreme heat. Vegetation responds to this climate by spreading dense forests, woodlands and shrublands over many regions that in later times will become cooler or more open. In the high northern latitudes, mixed broadleaf and conifer forests stand where later tundra will develop, and swamps and floodplain forests occupy lowlands near coasts and river mouths. Farther south, tropical and subtropical forests form thick canopies that intercept intense sunlight, while understory plants grow in the shaded, humid air. These plant communities draw carbon from the atmosphere, through photosynthesis build soils rich in organic matter, and help regulate local water cycles by returning moisture to the air through transpiration. Animal life also reflects the warm conditions. Early mammals, birds, reptiles, and a wide variety of smaller creatures occupy niches in forests, wetlands, and coastal environments. Many mammal groups are still relatively small in body size compared with some that will evolve later, but they are diverse and already experimenting with different ways of life in trees on the ground and in nearshore waters. Insects and other invertebrates thrive in the warm, moist climates of many regions, taking advantage of long-growing seasons and abundant plant material. In the oceans, plankton communities float in sunlit surface waters, where they capture energy and form the base of marine food webs. Their shells and organic remains sink slowly through the water column, feeding deeper organisms and contributing to the long-term burial of carbon in marine sediments. Warm waters support a variety of marine reptiles, fishes, and invertebrates adapted to stable, relatively high temperatures. Coral communities and other carbonate-producing organisms grow in clear, shallow seas where light penetrates to the seafloor, adding their skeletons to the slow construction of reefs and carbonate platforms. Across this early Cenozoic world, the climate system appears settled into a long-lasting greenhouse mode. The lack of great ice sheets means that sea level responds mainly to changes in the shape of ocean basins and the rate of seafloor spreading rather than to the growth and decay of continental ice. Without large expanses of reflective ice, more solar energy is absorbed by the surface, reinforcing the warm state. The hydrological cycle, the continuous movement of water through evaporation, condensation, and precipitation, operates more vigorously than in cooler climates carrying heat, poleward through clouds and storms. Yet despite this energetic water cycle, the overall pattern of climate remains relatively steady over the long spans of time that define the Paleocene. Small natural variations occur driven by slow changes in Earth's orbit and by gradual shifts in volcanic outgassing and weathering, but these changes stay within a range that the atmosphere, oceans, and biosphere accommodate without dramatic disruption. Sediments accumulating on the seafloor and in quiet basins on land record this period as one of consistent background warmth with chemical and physical signals that fluctuate gently about stable average conditions. Layers of mud, sand, and carbonate build up year after year and century after century, preserving subtle variations in grain size, fossil content, and mineralogy that reflect ordinary shifts in currents, productivity, and regional climate. Within these deposits, the ratios of different forms of carbon and oxygen in tiny shells track the temperatures and the composition of the water in which they form, capturing the character of a world that remains firmly in a greenhouse state over many hundreds of thousands of years. The carbon cycle in this warm early Cenozoic world is a slow, continuous exchange of carbon among the atmosphere, oceans, living organisms, soils, and rocks, and it holds the climate in a relatively stable state over very long time scales. Carbon enters the atmosphere mainly as carbon dioxide released from Earth's interior, where it has been stored in minerals and melts. Volcanic arcs above subduction zones, long ridges where plates pull apart on the seafloor, and broad regions of magmatic activity all vent carbon dioxide as gases rise through the crust and escape at the surface. This input is steady when seen on geological timescales, and it tends to change only gradually as plate motions shift the locations and intensities of volcanism. The atmosphere does not simply accumulate this carbon without limit. Chemical reactions at the surface of continents grouped under the term weathering draw carbon dioxide back out of the air. Weathering in this sense is the breakdown and alteration of rocks by water-dissolved substances and biological activity. Rainwater picks up carbon dioxide from the air, and from the shallow soils it passes through becoming slightly acidic. As it flows over and through rocks, this water reacts with minerals, especially silicate minerals that contain calcium, magnesium, sodium, and potassium. These reactions form dissolved ions that rivers carry to the ocean, where they eventually combine with dissolved inorganic carbon to form carbonate minerals such as calcite. In warm, wet conditions with abundant vegetation and active soils, weathering proceeds efficiently, and this helps balance volcanic emissions over long intervals. The oceans act as an enormous carbon reservoir that links the atmosphere and the solid Earth. Carbon dioxide dissolves into surface waters, forming a pool of dissolved inorganic carbon that is in active exchange with the air on timescales of years to centuries. Winds, waves, and currents mix the upper ocean and help keep this exchange near equilibrium for given temperatures and pressures. Over longer periods, circulation carries some of this carbon-rich water into the deep ocean, where it may remain isolated from the atmosphere for many hundreds to thousands of years before returning to the surface. Marine organisms make use of this dissolved carbon. Phytoplankton in the sunlit surface layer take up inorganic carbon during photosynthesis and build organic matter, which is then passed to zooplankton and higher trophic levels. A fraction of this organic material sinks into deeper waters as particles and as the remains of dead organisms. Some decomposes and releases carbon dioxide back into the deep ocean, while some reaches the seafloor and becomes buried in sediments. At the same time, many marine organisms build shells or skeletons of calcium carbonate using calcium and carbonate ions supplied by rivers and the sea. These carbonate structures accumulate on the seafloor when they're not completely dissolved in the water column, gradually forming thick layers of muds and oozes rich in microscopic shells. The depth in the ocean where carbonate dissolves more rapidly than it accumulates, often called the carbonate compensation depth, sets an important boundary. Above this level, carbonate sediments can pile up. Below it, carbonate tends to dissolve and not be preserved. In the early Cenozoic, this depth follows the balance between the supply of carbonate and the acidity of deep waters, which in turn depends on how much carbon the ocean holds and how vigorous circulation is. Over very long time spans the burial of both organic carbon and carbonate carbon in sediments removes carbon from the active surface cycle and transfers it into the rock reservoir. This slow removal balances the input from volcanoes and metamorphic reactions, closing the loop of the long-term carbon cycle. When climate is warm and rainfall intense, weathering reactions can speed up supplying more ions to the sea and encouraging more carbonate burial. This feedback acts like a stabilizing influence. A warmer climate can enhance the removal of carbon from the atmosphere and ocean, eventually drawing down carbon dioxide and cooling conditions, while a cooler climate can slow weathering and allow carbon dioxide to build up again. On the continents, vegetation and soils introduce an additional layer to this cycle. Plants take in carbon dioxide from the atmosphere through photosynthesis and store carbon in leaves, wood, and roots. When plant matter dies and decomposes, much of this carbon returns to the air or the shallow subsurface as carbon dioxide, but some may be preserved in soils or in peat and other deposits that can later transform into coal or other organic-rich rocks. Soil organisms, including microbes and small animals, continuously respire carbon dioxide as they process organic material, maintaining a dynamic exchange between organic carbon in the ground and the air above. This exchange is sensitive to temperature, moisture, and nutrient supply, all of which are influenced by the warm and humid climate of the Paleocene. In addition to the balance of total carbon, the carbon cycle carries a signature in the form of carbon isotopes. Carbon atoms come in slightly different masses, and the ratio between the heavier and lighter forms in carbon-bearing materials provides information about processes that move carbon between reservoirs. When organic matter is formed and buried, it tends to be relatively enriched in the lighter isotope, leaving the combined ocean and atmosphere slightly enriched in the heavier one. Over many tens to hundreds of thousands of years before the Paleocene-Eocene Thermal Maximum, the carbon isotope values recorded in fossils and in carbonate sediments fluctuate within a limited range that reflects a stable balance between burial and release of carbon. Small variations arise as climate shifts in response to slow orbital changes, as local productivity in the ocean waxes and wanes, and as regional erosion and deposition patterns adjust to evolving topography. However, the overall pattern is one of modest excursions around a long-term mean, indicating that the sizes of the main carbon reservoirs and the rates of exchange between them remain relatively steady. The deep ocean in this interval serves as both a buffer and a recorder. Because the combined mass of carbon in the deep ocean is large compared with that in the atmosphere, changes in atmospheric carbon dioxide are moderated by exchanges with ocean waters. Chemical reactions between dissolved carbon species and seafloor sediments also help to regulate the acidity of the ocean. If more carbon enters the system, and increases acidity dissolution of carbonate on the seafloor can release carbonate ions that partly neutralize the added carbon and gradually restore conditions that favor carbonate preservation. This feedback operates over timescales of thousands to tens of thousands of years. Taken together, the volcanic emissions, weathering reactions, biological uptake, sediment burial, and ocean buffering create a carbon cycle that during the early Paleocene maintains a relatively constant climatic background. Carbon moves ceaselessly among reservoirs, but the long-term averages of atmospheric carbon dioxide and global temperature remain within a range that the atmosphere, oceans, and biosphere have occupied for extended periods. In sediments now buried deep beneath the seafloor and within continental basins, the layered record of this steady cycling is preserved as alternating bands of carbonate-rich and carbonate-poor material, subtle shifts in organic content, and small regular changes in carbon isotope ratios that mark the quiet breathing of the carbon cycle in a greenhouse world. On the eve of the Paleocene-Eocene boundary, the arrangement of continents and oceans shapes the climate of the warm early Cenozoic planet in quiet but powerful ways. The great plates that carry continents continue to drift, but on human scales the land masses appear fixed, forming a pattern that controls wind's currents and the pathways along which heat and moisture travel. In the northern hemisphere, the North Atlantic Ocean is still relatively narrow. Greenland lies as a substantial land bridge between high northern latitudes and the northern Atlantic region positioned between North America and Europe. To the west, North America stretches from low subtropical latitudes to near the pole, its eastern margin edged by broad continental shelves and shallow seas. To the east, the combined mass of Europe and parts of Western Asia forms another continental block with low-lying coastal plains and inland basins that open toward marine gateways. Between these lands, the young North Atlantic holds warm surface waters that move northward along some margins and return southward at depth, helping to transport heat toward higher latitudes, though the exact patterns differ from those of later times when the basin becomes wider and more deeply connected. Farther south, the equatorial and subtropical regions are dominated by wide expanses of ocean. The legacy of the ancient Tethys realm persists as a broad band of warm water extending from the eastern margin of the Atlantic into what will become the Indian Ocean, bordered by fragments of continental crust that include parts of Eurasia, Arabia, and northern Africa. This band acts as a major conduit for the transfer of heat and moisture around the planet. Over its surface, intense solar radiation warms the upper layers of the sea, and evaporation loads the lower atmosphere with water vapor. Seasonal winds respond to temperature contrasts between land and ocean, giving rise to monsoon-like systems that bring alternating wet and dry periods to surrounding continental margins. South of the equatorial belt, the South Atlantic is wider than its northern counterpart but still smaller than in later ages. South America and Africa face each other across a growing ocean basin, whose seafloor is being created along a spreading ridge. Warm surface waters occupy much of this basin, while deeper currents carry mass and properties southward into higher latitudes. In the far south, Antarctica sits closer to the southern polar region, but at this time it is not yet encircled by a continuous deep water passage that would later support a strong isolated circumpolar current. Instead, shallow and semi-restricted gateways link the Southern Ocean to the South Atlantic, the Indian Realm, and perhaps to the Pacific. These partial connections allow a more direct exchange of heat between middle and high southern latitudes than in later intervals when a circumpolar flow thermally isolates Antarctica more completely. Australia lies farther south than it will in later times and remains closer to Antarctica, while India continues its northward journey through the low-latitude oceans toward eventual collision with Asia. In the vast region that will become the Pacific, a large ocean spreads across much of the globe, bounded by arcs of subduction zones and chains of island arcs. This ocean holds a large share of the planet's surface waters and acts as an enormous reservoir of heat and carbon. Winds blowing across its surface set up broad gyres with warm water, moving westward along the equator before turning poleward along western continental or island margins, and then returning equatorward at higher latitudes as cooler currents. These circulations are shaped by the positions of continents, and by the rotation of the planet, giving rise to patterns of warm and cool surface waters that influence the distribution of clouds, rainfall, and storm tracks. The atmospheric circulation above this arrangement of land and sea has a familiar but slightly altered structure compared with later climates. Near the equator, strong solar heating drives a belt of rising air, forming a warm, moist zone where tall convective clouds deliver frequent rainfall. From this belt, air flows poleward aloft, and then sinks in subtropical regions, creating high-pressure zones associated with drier conditions over some oceanic and continental areas. The resulting pattern of Hadley cells moves heat away from the equator and helps maintain the relatively small temperature contrast between low and high latitudes that characterizes the greenhouse world. At mid-latitudes, bands of westerly winds encircle the globe in both hemispheres. These westerlies steer storms that draw energy from the contrast between warm and cool air masses and between ocean and land. However, because polar regions are not deeply cold, and because sea ice and permanent snow cover are restricted or absent, the temperature gradients that feed these storms are less sharp than in later Ice Age climates. As a result, some storm systems may be broader and less intense, with more persistent cloudiness and steady rainfall rather than strong sudden frontal changes. Jet streams exist as narrow, fast-flowing currents of air at high altitudes, but their positions and strengths are influenced by the smoother distribution of surface temperatures and by the differing shapes of ocean basins and continental masses. The absence of a fully developed Antarctic circumpolar current means that cold, dense surface waters do not yet wrap efficiently around the southern high latitudes. Instead, relatively warm waters can approach Antarctic margins more readily, keeping coastal climates milder and helping forests and other vegetation persist at high southern latitudes. In the deep ocean, circulation patterns are governed by the formation of dense waters at the surface in certain regions and their subsequent sinking and spread along the seafloor. In this greenhouse climate, the waters that feed the deep ocean are warmer and saltier than in later cold intervals. Candidate regions for deep water formation include high southern latitudes and perhaps parts of the North Atlantic or the Tethyan corridors, where surface waters can be cooled enough or made salty enough through evaporation to become dense and descend. Once at depth, these waters move slowly along gradients in density, spreading through the abyssal basins and carrying with them dissolved nutrients, oxygen and carbon. The pathways and intensities of these deep flows are shaped by the contours of ocean basins, the positions of ridges and sills, and the overall density structure of the water column, all of which are set by the paleogeography of the time. Continental interiors experience climates that are moderated by the proximity of warm oceans, but still influenced by distance from the coast by elevation and by regional circulation patterns. Low-lying central regions of many continents enjoy long-growing seasons with relatively mild winters and warm summers, while higher plateaus and mountain belts experience cooler conditions and increased precipitation on windward slopes. Because sea levels are high, many continental margins host broad coastal plains and interior seaways that extend the influence of the ocean far inland. These shallow marine and marginal environments act as transition zones where marine and terrestrial processes meet, and they are sensitive recorders of changes in water depth, salinity, and sediment supply driven by both tectonics and climate. The combined effect of this continental and oceanic layout is a climate system in which heat is transported efficiently from low to high latitudes through both the atmosphere and the oceans. Warm currents stream along some coasts, bathing them in heat and moisture, while cooler waters upwell in other regions, supporting high biological productivity and influencing regional climates. Atmospheric circulation responds to this distribution by adjusting wind belts and storm tracks to the shapes of land and sea, producing a variety of regional climate regimes that range from persistently moist equatorial belts to seasonally dry subtropics and relatively mild high-latitude zones. All of these patterns rest upon the slow drift of plates and the steady background greenhouse forcing that has defined the early Cenozoic. Over geological time, the continued movement of continents will reshape basins and gateways, but in the interval just before the Paleocene-Eocene boundary, the world's geography and circulation have settled into a configuration that supports a broadly warm, equable climate with only gentle variations recorded in the sediments accumulating on land and in the depths of the oceans. As the Paleocene draws toward its boundary with the Eocene, the background stability of the greenhouse world begins to show subtle departures that are only clear when seen through the slow lens of geological records. In many marine and continental deposits, the layered archives that have quietly recorded small fluctuations now start to preserve signals of change that differ from the gentle variations of earlier millions of years. These signals do not yet mark an abrupt shift. Instead, they unfold as a gradual narrowing of conditions toward a threshold. In the deep sea, fine-grained sediments continue to settle on the ocean floor, carrying the remains of plankton, tiny shells and particles washed from distant continents. Within these sediments, the ratios of the lighter and heavier forms of carbon in carbonate shells which have traced the breathing of the carbon cycle begin to drift slightly toward lighter values over intervals of many tens of thousands of years. The change is modest at first, not a sharp step, but a slow lean, indicating that more carbon with a lighter isotopic signature is entering or moving through the ocean atmosphere system than before. At the same time, in some regions, the oxygen isotope composition of these same shells hints at a gentle rise in temperatures or a shift in the balance between surface and deep waters, though the exact magnitude and timing vary from basin to basin. The seafloor itself, especially in the deeper parts of the ocean, continues to mark the boundary between depths where carbonate sediments can accumulate and depths where they dissolve. As the composition of deep waters responds to the early stages of change in the carbon system, this boundary may begin to move upward in some places, suggesting a slow increase in acidity. However, this motion is not yet dramatic. Carbonate-rich layers still form over wide areas, and the deep ocean retains much of its buffering capacity. These slow adjustments etched into these depths are subtle precursors, delicate shifts in a system that has long balanced volcanic inputs, weathering and burial. On continental margins and in interior basins, the story unfolds through changes in facies, the recognizable packages of sediments that reflect particular environments. Paleosols, the ancient soils preserved within sedimentary sequences, record shifts in weathering intensity and in the interplay between rainfall and evaporation. In some regions, these soils show increasing development of clay minerals that form under warm, wet conditions, pointing to strengthened chemical weathering and perhaps to more persistent or intense rainfall. River deposits shift in character, with some systems displaying changes in grain size, channel pattern, or floodplain extent that suggest adjustments in runoff and sediment supply. Lakes expand or contract, leaving behind sequences of muds, evaporate layers, or organic-rich beds that trace evolving water budgets in continental interiors. Vegetation captured in the fossil record as leaves, pollen grains, spores, and wood responds to these shifts in climate and hydrology. In high-latitude regions that have long hosted forests under the mild greenhouse climate, plant assemblages adjust as temperature and moisture regimes evolve. Some taxa with preferences for warmer or more humid conditions become more common, while others that favour slightly cooler or drier environments retreat or become less abundant. In lower latitude regions, tropical and subtropical floras experience changes in the relative dominance of plant groups, with certain lineages expanding along newly favourable climate corridors. These botanical responses do not yet represent a wholesale reorganisation of ecosystems, but they reflect the sensitivity of living communities to even modest climatic trends. In shallow marine environments near coasts, carbonate-producing organisms and sedimentary structures continue to build reefs, banks and platforms, yet the balance between carbonate and siliciclastic input can shift as weathering and runoff patterns on land adjust. Increased delivery of fine clays and other materials from rivers may locally reduce water, clarity influence the distribution of benthic communities, and change the textures of accumulating sediments. In some settings, organic rich layers develop where productivity in the surface waters and restricted circulation in bottom waters combine, hinting at evolving nutrient cycles and oxygen levels. Throughout these environments, the early stages of the approach to the Paleocene-Eocene boundary are recorded as gentle but persistent trends. The carbon isotope values in both marine and terrestrial archives, which have fluctuated around relatively stable means for long intervals, start to drift downward more consistently. This behavior indicates that more carbon with a light isotopic composition, characteristic of organic carbon or certain geological reservoirs, is becoming part of the active surface cycle. The source of this carbon may involve a combination of processes, and the precise contributions remain a subject of investigation, but the net effect is a slow adjustment of the isotopic baseline that sets the stage for more pronounced changes that will follow. The timescales over which these precursory signals develop are still long compared with human experience, spanning many thousands to perhaps tens of thousands of years. Yet in the context of Earth history, they are relatively rapid. The climate system, with its interconnected atmosphere, oceans, and biosphere, responds to the evolving carbon balance through gentle warming that adds to the already elevated temperatures of the greenhouse world. regional climates experience shifts in seasonal patterns in the frequency and intensity of rainfall events and in the distribution of dry and wet zones. Some areas become more prone to heavy precipitation and flooding, while others may experience longer dry intervals between storms. These changes feed back into weathering and erosion, altering the delivery of ions and sediments to the oceans, and closing loops in the carbon and sediment cycles. High-latitude regions where mild conditions have long allowed forests and wetlands to persist absorb part of this additional warmth. Growing seasons may lengthen further, and cold season temperatures rise, reducing the frequency of frost and altering the balance between plant growth and decomposition. Wetlands and peat-forming environments respond as water tables and temperature regimes shift, influencing the accumulation and preservation of organic matter. These changes in turn affect the release or storage of carbon in continental reservoirs. At the same time, the geometry of ocean basins and seaways continues its slow evolution under plate tectonic forces. Magmatic activity in some regions may increase associated with the development of large igneous provinces or with changes in spreading rates along mid-ocean ridges. Such activity can influence both the direct emission of carbon dioxide and the supply of fresh, easily weathered rock surfaces that draw down carbon through chemical reactions. In the lead-up to the Paleocene-Eocene boundary, the net outcome of these interacting processes is a climate and carbon cycle that remain recognizably similar to the earlier Paleocene state, yet display clear signs of drift. The sediments accumulating at this time preserve a quiet convergence toward a boundary that is not yet crossed but is approaching. Layer by layer they record a world in which the background greenhouse warmth is beginning to intensify, the isotopic composition of carbon in the ocean and atmosphere is slowly shifting, and ecosystems on land and in the sea are adjusting to these trends in ways that are subtle in the moment but unmistakable when read from the vantage point of millions of years later. When the Paleocene-Eocene boundary is finally reached, the quiet trends that have been building in the climate and carbon system give way to a more abrupt change that stands out sharply in geological records. In marine sediments around the world, from deep ocean basins to continental margins, the tiny carbonate shells that have tracked the balance of carbon isotopes suddenly show a marked shift toward lighter values. This shift, described as a negative carbon isotope excursion, signals a rapid addition of carbon that is relatively enriched in the lighter isotope into the combined ocean-atmosphere reservoir. The change unfolds over a geologically short interval, on the order of several thousands of years or less, which is extremely rapid when compared with the slow variations that preceded it. In cores taken from deep-sea drilling sites, the layers that span this boundary show a sharp downward step in the isotopic composition of carbonate. Above a horizon that reflects late Paleocene conditions, the carbon isotope ratios in planktonic and benthic foraminifera, in bulk carbonate, and in some cases in organic matter itself, drop by several parts per thousand relative to earlier values. The precise magnitude of the shift varies among locations and materials, with some terrestrial records indicating even larger excursions, but the global pattern is consistent, a clear rapid movement toward lighter isotopic signatures that cannot be explained by ordinary fluctuations in productivity or regional carbon cycling. At the same time, in many sedimentary sequences, the boundary interval is marked by distinctive lithological changes. In some deep ocean sites, a thin clay-rich layer interrupts the more usual carbonate-dominated sequence. This clay horizon often corresponds to the level where the negative carbon isotope excursion begins and where carbonate content falls sharply, indicating that conditions in the deep ocean briefly became corrosive enough to dissolve much of the carbonate passing through the water column, or sitting on the seafloor. In shallower settings above the depth where carbonate normally dissolves, carbonate sedimentation continues, but even there the isotopic shift is recorded in the shells of organisms living in surface and intermediate waters. Terrestrial records preserved in continental margin sequences lake deposits and paleosols also capture the onset of the excursion. The carbon isotopic composition of soil carbonates, plant material and organic rich layers shows a similar sharp move toward lighter values, though the exact shapes and sizes of these changes vary with local conditions and with the ways in which different archives integrate carbon signals. Fossil plant assemblages and pollen spectra, while primarily reflecting vegetation, can be associated with these isotopic markers, helping to align continental and marine records. Together, these observations show that the input of light carbon is not confined to one region, but affects the entire interconnected surface system. The source of this additional carbon must have an isotopic signature that is significantly lighter than that of the pre-event ocean atmosphere reservoir. Candidate sources include carbon stored as organic matter in sediments and soils, methane bound in marine or permafrost-like settings, and carbon dioxide released by certain volcanic or thermal processes. Each of these reservoirs carries a characteristically light isotopic composition compared with the combined ocean and atmosphere. The rapidity and magnitude of the excursion imply that a very large mass of carbon, on the order of many thousands of petagrams, enters the active system over a relatively short interval. While the exact partitioning among sources and the precise release rates remain subjects of research and debate, the record clearly indicates that the balance between long-term inputs and removals of carbon has been temporarily but strongly disturbed. As this light carbon enters the atmosphere, the partial pressure of carbon dioxide rises, enhancing the greenhouse effect beyond the already elevated background of the early Cenozoic. The atmosphere responds by trapping more outgoing long-wave radiation, and the energy balance of the planet shifts toward higher temperatures. Because the deep ocean contains a large mass of dissolved carbon, it plays a crucial role in spreading and diluting the isotopic signal. However, the initial perturbation is strong enough that even as the ocean takes up carbon from the atmosphere, the combined reservoir retains a markedly lighter isotopic composition. The surface ocean, which exchanges carbon rapidly with the air, records the onset of the excursion in the shells of planktonic foraminifera and in the skeletal material of other carbonate-producing organisms. As newly formed shells incorporate dissolved inorganic carbon from the surrounding water, they lock in the shifted isotope ratios, preserving a detailed profile of the change in the layers that accumulate on the seafloor. In the deep ocean, where waters exchange more slowly with the surface, the isotopic signal spreads as circulation carries surface-modified waters downward and along basin floors. This spread is recorded in the remains of benthic foraminifera, which live at or near the sediment-water interface. In many locations, the carbon isotope excursion in benthic species appears nearly as sharp as in surface dwellers, indicating that the release of light carbon and its redistribution occur rapidly compared with deep water mixing timescales. The accompanying change in ocean chemistry is expressed not only in isotope ratios, but also in the physical preservation of carbonate. As more carbon dioxide dissolves in seawater, it forms carbonic acid, which lowers pH and shifts the balance among dissolved carbon species. The result is a decrease in carbonate ion concentration, especially in deeper waters. Because carbonate minerals dissolve more readily when carbonate ion levels fall, the depth at which dissolution outpaces accumulation rises toward shallower levels. In sedimentary records, this shoaling carbonate compensation depth is visible as a transition from carbonate-rich to carbonate-poor or clay-rich intervals sometimes accompanied by changes in color and texture that reflect the loss of carbonate components. On land, the atmosphere carrying the added carbon dioxide and the warming it produces begins to modify conditions in soils and vegetation. The isotopic composition of atmospheric carbon dioxide itself shifts toward lighter values as the new carbon is mixed into the air. Plants that use this carbon during photosynthesis inherit this isotopic signal, and their tissues record it. When these tissues fall, decay, and become part of soils or are preserved in sediments, the shift is captured in organic matter and in some soil carbonates that form in equilibrium with soil CO2. This allows geoscientists to trace the excursion in continental settings and to match it to the marine record, revealing a nearly synchronous change that spans both realms. The timescale of onset is an important aspect of this layer of the Paleocene-Eocene Thermal Maximum story. Different records and modelling studies suggest that the main phase of the isotopic shift and associated carbon release occurs over a short interval, possibly within a few thousands of years or less, though exact values differ among reconstructions. This rapidity distinguishes the event from slower orbitally paced variations and points to a trigger or combination of triggers capable of injecting large amounts of carbon quickly. While the details of these triggers remain incompletely resolved, the geological evidence leaves little doubt that the system experiences a strong abrupt forcing that drives it away from its previous equilibrium. In the immediate wake of the onset, the climate system begins to adjust toward a new warmer state. Temperatures measured indirectly from oxygen isotopes in marine carbonates, from certain organic molecules that respond to water temperature, and from plant proxies on land rise in step with or shortly after the carbon isotope excursion. The amplitude of warming adds several degrees Celsius to an already warm world, though the precise magnitude varies with latitude and environment. This warming, however, and the full expression of its consequences in atmospheric circulation, hydrological cycles and ecosystems, belong to the next layer of the story. At the level of the onset itself, the defining features are the rapid global shift toward lighter carbon isotopic values, the large and sudden addition of light carbon to the ocean, atmosphere system and the associated initial changes in ocean chemistry and sedimentation that together mark the start of the Paleocene-Eocene Thermal Maximum. As the large release of light carbon continues after its abrupt onset, the climate system of the early Cenozoic planet moves into a new phase in which rapid global warming takes firm hold. Against the backdrop of an already warm greenhouse world, this additional forcing raises temperatures by several degrees Celsius on a timescale that is short in geological terms. In marine records, oxygen isotope measurements from the shells of planktonic and benthic foraminifera shift toward values that correspond to warmer water, and this shift accompanies or closely follows the negative carbon isotope excursion that marks the injection of light carbon. The change is not a gentle drift, but a comparatively steep transition in many sections, indicating that both surface and deep ocean waters are warming over only a few thousand years. Terrestrial archives tell a similar story. Fossil leaves in some regions display changes in their shapes and margins that, when interpreted through relationships between leaf traits and climate, point toward higher mean annual temperatures. Soil carbonates and certain organic compounds preserved in paleosols and lake sediments also register warmer conditions. These independent lines of evidence support the picture that global average temperatures rise by several degrees Celsius during the Paleocene-Eocene Thermal Maximum, superimposed on the already elevated values of the late Paleocene. The warming is not uniform everywhere, and estimates of its magnitude vary with latitude and environment. Many reconstructions indicate that high-latitude regions, which are already mild in the late Paleocene experience, particularly strong warming with temperatures increasing by several additional degrees, and perhaps more in some continental interiors and coastal zones. In the polar oceans, sea surface temperatures that were already temperate shift toward values that today would be associated with subtropical waters, and this leads to truly ice-free conditions in many, perhaps most high-latitude marine settings. At lower latitudes, where temperatures start from higher baselines, the increase may be somewhat smaller in absolute terms, but still sufficient to push tropical and subtropical seas and land areas to very warm conditions. In the deep ocean, benthic foraminiferal records indicate that waters far below the surface also warm by several degrees Celsius. This is notable because deep ocean temperatures respond to changes in the properties of surface waters that sink and fill the abyssal basins, and these responses typically occur over long timescales. During the Paleocene-Eocene Thermal Maximum, the warming of deep waters appears relatively rapid, suggesting that the properties of the source regions for deep water formation shift quickly, and that circulation patterns efficiently communicate the new thermal state throughout the deep ocean. The difference between surface and deep temperatures, already modest in the greenhouse world, may narrow further, reinforcing the impression of a more uniformly warm ocean interior. In the atmosphere, the additional carbon dioxide increases the radiative forcing of the climate system. More of the long-wave radiation emitted by Earth's surface is absorbed and re-emitted by greenhouse gases, raising the level in the atmosphere from which most heat escapes to space. To restore balance between incoming solar energy and outgoing radiation, the system adjusts by warming until the enhanced greenhouse effect is offset by increased thermal emission at higher temperatures. Water vapor itself, a greenhouse gas, responds to this warming as well, since warmer air can hold more moisture. This amplifies the initial temperature increase in a well-understood feedback. Clouds, which both reflect incoming sunlight and trap outgoing heat, also respond, though their net effect depends on changes in height, thickness, and geographical distribution. The overall outcome, as recorded in proxy data and supported by model studies, is a planet that moves into a significantly hotter state within a time span that is short, compared with the gradual changes driven by orbital variations. From the perspective of Earth history, the Paleocene-Eocene Thermal Maximum is therefore often described as a hyperthermal event, brief but intense interval of global warming added on top of the long-term greenhouse climate of the early Cenozoic. The term emphasizes both the rapid onset and the relatively limited duration of the peak warmth, compared with the millions of years over which background conditions evolve. In this context, rapid still means many thousands to tens of thousands of years, but this is fast enough that the response of many components of the Earth system is governed more by transient adjustment than by slow, near-equilibrium evolution. Seasonal cycles continue, but they are now superimposed on a warmer baseline. Winters at mid and high latitudes become milder, with fewer or shorter episodes of frost and snow, while summers occur in atmospheres that start from higher average temperatures and contain more water vapor. Nights cool from warmer daytime values, so minimum temperatures rise along with the daily maxima. Many biological and physical processes that depend on thresholds in temperature, such as the timing of plant growth soil, microbial activity, and certain aspects of weathering, are pushed into new regimes. The pattern of warming also has vertical structure in the atmosphere. The troposphere, the lowest layer where weather occurs, thickens as temperatures increase, because warmer air expands and the height at which the pressure falls to a given value rises. The lapse rate, or the rate at which temperature decreases with height, adjusts to the new moisture content and stability conditions, and this affects convection and cloud formation. At some heights, increases in greenhouse gases can lead to cooling, rather than warming, particularly in the stratosphere, because enhanced emission of radiation to space dominates. However, the main concern for the surface climate lies in the warming troposphere and in the way this altered thermal structure reshapes circulation patterns and the global distribution of heat. The energy content of the climate system increases as heat accumulates in the oceans and atmosphere. The upper ocean in particular stores a large fraction of the added heat. Raising its temperature and altering density contrasts both horizontally and vertically. These changes begin to influence currents and stratification, setting the stage for further adjustments in how heat and carbon are transported within the ocean. At the same time, the warmer atmosphere holds more moisture, so the total amount of water moving through evaporation and precipitation increases. This intensification of the hydrological cycle, though still to be expressed in specific regional patterns of rainfall and dryness, is an inevitable consequence of a warmer, wetter air column. In geological archives, the combined effect of this rapid global warming is registered as a suite of correlated signals. Carbon isotopes indicate the addition of light carbon-oxygen isotopes in carbonates, and other temperature-sensitive proxies record higher temperatures, and sedimentary features capture associated changes in weathering runoff and biological productivity. The alignment of these signals in time across many regions and environments strengthens the interpretation that the Paleocene-Eocene Thermal Maximum represents a coherent climatic event, rather than a loose collection of unrelated local changes. The planet's climate system, nudged by the large injection of carbon, has moved decisively away from its previous equilibrium and into a warmer, more energetic state. The detailed structure of this new state, in terms of how heat is distributed between equator and poles, between land and sea, and between surface and deep layers of the atmosphere and ocean, belongs to the next layer of the story. But the defining feature of this stage is clear. Rapid global warming has taken hold and now governs the evolution of the Paleocene-Eocene Thermal Maximum. At the peak of the Paleocene-Eocene Thermal Maximum, the atmosphere of the planet holds more heat and moisture than at any earlier time in the Cenozoic record so far, and the distribution of this heat across latitudes and altitudes takes on a distinctive pattern. The added carbon dioxide and other greenhouse gases strengthen the trapping of outgoing long-wave radiation, and the surface and lower atmosphere respond with higher temperatures from equator to poles. Yet the increase is not evenly spread. High-latitude regions, which started from a mild baseline in the late Paleocene, warm strongly, while low-latitude regions already warm gain less in relative terms. The result is a reduction in the equator to pole temperature gradient, a more evenly warmed world, in which contrasts between tropical and polar climates become smaller than in many other intervals of Earth history. In polar oceans, surface waters that were once cool now reach temperatures that in later climates would be associated with subtropical conditions. Evidence from marine microfossils and other temperature proxies indicates that these high-latitude seas may sit at temperatures of well over 10 degrees Celsius, and perhaps considerably above that in some regions. On nearby land masses, forests extend to very high latitudes, supported by warm air masses and the absence of permanent ice. Winters remain mild, summers are warm, and the annual cycle of temperature becomes less extreme than in climates with strong seasonal cooling. Moving toward mid-latitudes, continental interiors and coastal zones also experience elevated temperatures. The contrast between oceanic and continental climates persists, but warm seas surrounding many land masses soften the transitions. Sea breezes carry moist, warm air inland, while the lack of extensive ice and snow cover reduces the reflection of solar radiation, allowing more energy to be absorbed by the surface. In these belts, the difference between summer and winter temperatures is still present, but damped compared with cooler worlds, and nights cool from higher daytime values, so minimum temperatures rise along with maxima. Near the equator, sea surface temperatures and air temperatures are already high before the event, and the additional warming may be more limited in absolute terms than at higher latitudes. Even so, the tropical atmosphere becomes more moisture-laden and energetically charged. The belt of rising air near the equator, where warm humid air ascends and condenses to form deep clouds, continues to act as a major engine of the climate system. With higher temperatures and more water vapor, this ascending region may widen or intensify, spreading its influence over a broader span of latitudes and supporting more frequent or more persistent convective activity. The pattern of heat distribution in the atmosphere remains organized into large cells. The Hadley cells, which transport energy poleward from the equator, operate in a warmer, thicker troposphere. As air rises in the equatorial belt and moves toward higher latitudes aloft, it carries more latent and sensible heat than before. When it descends in the subtropics, it warms and dries, helping to maintain or expand belts of relatively low precipitation between the wet equatorial and mid-latitude zones. However, because the overall temperature contrast between low and high latitudes is reduced, some of the sharpness of boundaries between circulation regimes may soften, and storm tracks may shift their positions in response. The jet streams that mark the boundaries between different air masses respond to these changes in temperature gradients. In a climate with weaker equator to pole contrasts, jets may be less intense or may migrate in latitude, altering the preferred paths of mid-latitude storms. The westerly winds that encircle the globe in both hemispheres continue to guide low-pressure systems and associated fronts, but the thermal contrasts that feed their growth differ from those in cooler times. Storms may become more widespread and slow-moving, with longer-lasting periods of cloudiness and rain in some regions, while sharp temperature jumps across fronts become less pronounced. In the vertical dimension, the structure of the atmosphere adjusts to the added heat. The troposphere expands, and the height of the boundary between the troposphere and the stratosphere rises, especially in the tropics where heating is strongest. Temperature decreases with height through a deeper layer, and the location where clouds reach their maximum altitude shifts accordingly. Convection develops in this expanded space, distributing heat and moisture through a greater depth. Water vapor content rises throughout the troposphere, increasing both the greenhouse effect and the amount of latent heat available to drive storms. High clouds made largely of ice, and lower clouds composed of liquid droplets. Both influence the balance between reflection of sunlight and trapping of outgoing radiation. Small changes in their distribution and properties can have important effects on local and regional climates, but the general picture remains one of a cloudy, moisture-rich atmosphere under strong greenhouse forcing. Over the oceans, the pattern of sea surface temperature strongly shapes the overlying air. Warm pools of surface water support deep convection and heavy rainfall, while relatively cooler upwelling zones anchor regions of lower cloud tops and stratiform clouds. During the Paleocene Eocene Thermal Maximum, the contrast between the warmest and coolest ocean surfaces likely narrows, but regional variations still exist where currents bring cooler waters to the surface, or where winds drive strong evaporation. These sea surface patterns in turn anchor atmospheric circulation. Features such as tropical convergence zones and subtropical high-pressure cells. Over continents, the distribution of heat depends on proximity to oceans' elevation and land cover. Coastal regions, especially those adjacent to warm currents, experience humid, warm conditions with relatively small annual temperature ranges. Interiors, particularly at low to mid-latitude, still face hotter summers and potentially stronger seasonal swings in rainfall, but even there winters remain warmer than in many other geological periods. Elevated terrains provide some relief from heat, as temperatures decrease with altitude, and these highlands may host climates that differ from surrounding lowlands despite the general warmth. The reduced equator to pole temperature gradient has important consequences for the overall distribution of energy in the climate system. In climates with strong gradients, much of the transport of heat from low to high latitudes is carried by vigorous eddies and storms in the mid-latitudes. In the Paleocene-Eocene Thermal Maximum with smaller gradients, the balance between large-scale overturning circulations and smaller-scale eddies shifts. The Hadley circulation and associated monsoon systems may carry a larger fraction of the poleward heat transport, while individual storm systems operate in an environment with weaker contrast to draw upon. This does not eliminate storms, but it changes their character and the patterns of cloudiness and precipitation they produce. In high latitudes, the absence of large areas of bright reflective ice and seasonal snow means that more solar energy is absorbed during the long days of polar summers. Dark ocean waters and vegetated land surfaces soak up sunlight that in colder climates would be reflected back to space. This additional absorption reinforces local warming and helps maintain the warm conditions that allow forests and other vegetation to thrive near the poles. As a result, the planet's albedo or average reflectivity is lower than in ice-rich worlds, and this lowers the threshold of greenhouse forcing required to sustain high temperatures. At night and during polar winters, the thick, moist atmosphere and warm oceans moderate cooling, so temperatures drop from elevated baselines rather than from very low starting points. The atmosphere during peak Paleocene-Eocene thermal maximum conditions is thus not only warmer but also more uniform in some respects. Longitudinal differences tied to the distribution of land and sea persist, but latitudinal contrasts in temperature and in many regions in humidity diminish. The climate system operates with a high energy content and an active hydrological cycle, continually moving heat and moisture through a layered atmosphere that has adjusted its structure to the new thermal state. While local climates vary in their specific responses, the overarching pattern of peak conditions is a strongly greenhouse-warmed world with a reduced equator to pole temperature gradient and a thick, moisture-laden atmosphere that redistributes heat efficiently across the globe. At the peak of the Paleocene-Eocene thermal maximum, the surface oceans hold a great store of heat, and this warmth spreads widely across basins that already sit in a greenhouse climate. Sea surface temperatures rise by several degrees Celsius relative to late Paleocene values, and this increase is recorded in the shells of plankton that grow in the thin sunlit layer near the top of the ocean. In high-latitude seas that were previously cool, but ice-free surface waters now reach temperatures that today would be considered distinctly temperate or even subtropical. In low-latitude regions where the ocean is already warm, temperatures climb further, approaching levels at which even small additional increases have important consequences for density stratification and the exchange of heat and gases with the atmosphere. The result is a set of surface waters that are warm almost everywhere, with smaller contrast between equator and poles than in many other times, yet still arranged in patterns shaped by wind currents and basin geometry. The vertical structure of the upper ocean responds strongly to this added heat. Warm water is less dense than cooler water, so when surface layers warm, they tend to sit more stably, above cooler, denser layers beneath. This stability strengthens stratification, especially in low and mid-latitude regions where solar heating and high air temperatures support persistent warm surface layers. The mixed layer, the zone where wind and waves churn the water and keep temperature and salinity relatively uniform, may become shallower in some regions as the density difference between the surface and the underlying water increases. In others, strong winds and storms can still stir heat downward, but they do so into water that starts from warmer initial conditions. Overall, the boundary between the well-mixed surface and the more quiescent waters below becomes an important feature of the peak Paleocene-Eocene Thermal Maximum ocean, maintaining a sharp transition in temperature and sometimes in salinity. This stratification has consequences for the way nutrients move into the sunlit zone that supports most marine photosynthesis. In many modern analogues, upwelling of cooler nutrient-rich water from below the thermocline supplies nitrogen, phosphorus, and other elements that phytoplankton require. During the Paleocene-Eocene Thermal Maximum, the strong density contrast between warm surface water and cooler, deeper water can make it more difficult for mixing processes to transport these nutrients upward in some basins. Where winds and currents do drive up welling, the water that reaches the surface is warmer than in cooler climates, and its chemical composition has been influenced by the altered balance of respiration, remineralization, and circulation in the subsurface ocean. In some regions, productivity may decline if nutrient supply is reduced, while in others, local circulation patterns and coastal processes still sustain active upwelling systems. The pattern is therefore not uniform, but the general tendency towards stronger stratification is a key element of the surface ocean response to extreme warmth. Ocean currents at the surface continue to organize themselves into large gyres under the influence of winds and the rotation of the planet. In the vast basin that occupies much of the region that will later be called the Pacific trade winds, blow from east to west near the equator, piling warm surface waters into the western parts of the basin and lowering sea surface height slightly in the east. Along the western margins of continents or island arcs, warm currents carry heat poleward, bathing coasts in high temperatures and humidity. On the eastern sides, cooler currents or zones of upwelling moderate conditions. Somewhat though, even these regions now sit in a climate that is warmer than before the event. Similar patterns occur in the developing Atlantic and Indian realms, though the shapes of the basins and the positions of continents impose their own geometries on the gyres. These surface currents not only redistribute heat, but also carry dissolved gases, nutrients, and organisms over long distances, linking distant coasts and open ocean regions in a moving network. The higher temperatures of the surface ocean influence its interaction with the atmosphere in several ways. Warm water evaporates more readily, so evaporation rates over many regions increase, loading the lower atmosphere with water vapor. This vapor is transported by winds, and later condenses as precipitation connecting oceanic evaporation zones with continental rainfall belts through the intensified hydrological cycle. At the same time, the ability of seawater to hold dissolved gases, including carbon dioxide and oxygen, decreases with warming. Surface waters therefore tend to exchange these gases with the atmosphere in ways that depend on local concentrations, wind speeds, and the balance between biological production and respiration. In parts of the ocean where photosynthesis draws down carbon in the surface and transports it into the interior, the sea continues to act as a sink for some of the excess carbon dioxide in the atmosphere, even in warmer conditions. Elsewhere, upwelling of carbon-rich deep water or other processes can cause the ocean to release carbon dioxide back to the air. The net effect during the Paleocene-Eocene Thermal Maximum is a dynamic exchange in which the ocean both moderates and participates in the evolving greenhouse state. Warmer surface waters also alter the patterns of sea surface salinity. Evaporation removes water but leaves salts behind, increasing salinity in some subtropical and mid-latitude regions, where evaporation exceeds precipitation and river input. In contrast, areas near the equator and in certain high-latitude zones may experience enhanced rainfall that freshens the surface. Meltwater from any remaining small ice stores or from increased river discharge can also reduce salinity locally. These salinity patterns combined with temperature set the density structure of the surface and near-surface ocean, and therefore influence where waters become dense enough to sink and contribute to deeper circulation. In a world with strong surface warming, some traditional sites of deep water formation may weaken, while others, especially in regions where cooling and evaporation still produce dense water, may remain active or adjust in depth and intensity. Sea level already high in the early Cenozoic greenhouse climate, due to the absence of large continental ice sheets and the thermal expansion of warm ocean waters, responds further to the added heat. As the surface and upper ocean warm, the water expands slightly, raising global mean sea level by additional amounts. Though this expansion is modest when expressed per degree of warming, the vast volume of the oceans means that even small fractional changes translate into noticeable increases. High sea levels inundate low-lying continental margins, extend shallow epicontinental seas into interior regions, and create broad, warm coastal shelves where light penetrates to the seafloor. These shelves host diverse communities and serve as important zones of carbonate and clastic sedimentation, but they are also sensitive to changes in water depth temperature and circulation associated with the Paleocene-Eocene Thermal Maximum. Regional patterns of surface ocean temperature structure the climates of nearby land masses. Coasts along warm western boundary currents experience hot, humid conditions with sea breezes that carry moisture inland and support frequent rainfall. Eastern boundary or upwelling influenced coasts may have slightly cooler waters and more stable marine layers, but even these areas sit in a warmer oceanic environment than before the event. The contrast between maritime and continental climates persists, but warm seas damp temperature extremes near coasts and feed moisture into the atmosphere that later precipitates over interiors. The character of marine storms that draw energy from warm surface waters also reflects this heat reservoir. In a warmer world with high sea surface temperatures and abundant water vapor, the potential intensity of convective systems increases. However, the large-scale organization of such storms depends on wind shear atmospheric stability and other factors that are set by the broader circulation. The geological record does not provide a direct detailed catalogue of individual storms, but the combination of warm water, high humidity, and an energetic atmosphere indicates that surface oceans during the Paleocene-Eocene Thermal Maximum contribute significantly to the vigor of the hydrological cycle. Despite these dynamic processes, the surface ocean at peak warmth remains governed by physical principles that seek balance. Heat entering from solar radiation is redistributed by currents mixed downward by winds and waves and eventually lost to the atmosphere and space. Evaporation and precipitation cycles exchange fresh water between ocean and land. Biogeochemical processes in the surface layer take up and release nutrients and carbon. Under the extreme but still orderly conditions of the Paleocene-Eocene Thermal Maximum, these processes operate in regimes shifted toward higher temperatures and stronger stratification, but they do not cease to follow the same basic rules. The surface ocean thus becomes both a reservoir of excess heat and an active participant in moving that heat around the globe, setting the stage for how deeper waters, marine chemistry and life in the ocean interior respond in the layers that lie below. In the depths of the oceans during the Paleocene-Eocene Thermal Maximum, the response to added carbon and surface warming becomes most clearly expressed as a combination of acidification, carbonate dissolution, and changes in seafloor communities. The same carbon dioxide that accumulates in the atmosphere and warms the climate also dissolves into seawater, increasing the total amount of dissolved inorganic carbon in the ocean. When carbon dioxide reacts with water, it forms carbonic acid, which dissociates and releases hydrogen ions. These ions combine with carbonate ions that would otherwise be available to form calcium carbonate minerals, lowering the concentration of carbonate ions and making it more difficult for carbonate to remain stable, especially at high pressures in the deep ocean. The measure that captures this tendency, the saturation state of calcium carbonate, declines in many deep basins. As the saturation state falls, existing carbonate shells and sediments become more prone to dissolution, and new carbonate particles sinking from the surface are more likely to dissolve before or shortly after reaching the seafloor. The depth at which dissolution of carbonate outpaces its accumulation, the carbonate compensation depth shoals towards shallower levels. During the Paleocene-Eocene Thermal Maximum, evidence from deep-sea drilling shows that this shoaling is substantial. In some regions, sites that previously lie above the depth, where carbonate dissolves, now sit within waters that are chemically corrosive to carbonate, so that carbonate-rich sediments are replaced by clay, rich layers, or by sediments with much lower carbonate content. Cores from such sites often show a transition from light-coloured carbonate oozes below the event interval to darker, more clay-dominated material within it, sometimes overlain by carbonate-rich layers higher in the sequence. Within the event interval itself, the fine fraction of carbonate may be almost absent, leaving a residue of non-carbonate particles and the more resistant parts of larger shells and skeletons. In other locations where water depths are shallower, or where the chemistry of deep and intermediate waters differs, carbonate never fully disappears, but still records a marked reduction in preservation. Shells appear more etched and fragmented, and the proportion of carbonate in the sediment decreases compared with levels before the event. This spatial pattern reflects both the regional structure of ocean circulation and the varying depths of the seafloor. Deep basins and ridges experience stronger dissolution, while some shoulder regions on continental margins and mid-ocean highs retain partial carbonate cover. The acidification of deep waters unfolds over timescales, controlled by the mixing of the ocean. As surface waters loaded with additional carbon dioxide are subducted or sink in high-latitude regions, they carry their chemical signature into the interior. Circulation spreads these waters along density surfaces into the deep Atlantic, Pacific and Indian basins. Because the event involves a large addition of carbon, the buffering capacity of deep-sea sediments is temporarily overwhelmed in many places, and dissolution of carbonate on the seafloor proceeds until enough carbonate has been removed to neutralize part of the added acidity. This process gradually restores the saturation state, but during the peak of the Paleocene-Eocene Thermal Maximum, the imbalance persists long enough to leave a distinct stratigraphic mark. The deep ocean during this interval is not only more acidic but also warmer than before. Benthic foraminifera small-shelled protists that live at or near the sediment surface record both aspects of this environment. Their oxygen isotope compositions indicate warmer bottom water temperatures, while their carbonate shells show the imprint of the lowered saturation state through reduced preservation, and in many taxa through reduced survival. The fossil record of benthic foraminifera across the event shows a significant extinction of species, especially those adapted to the cooler, more stable conditions of the late Paleocene deep sea. Many taxa decline sharply in abundance or disappear entirely from the record, while a smaller set of more tolerant or opportunistic forms persists and later diversifies. This turnover reflects a deep-sea ecosystem stressed by the combined effects of warming acidification and possible changes in food supply and oxygen levels. The delivery of organic matter to the seafloor, which feeds benthic communities, may change as surface productivity and export flux respond to altered stratification and nutrient cycling. In some regions, increased stratification could reduce the upward supply of nutrients and lower productivity, while in others, shifts in circulation or coastal upwelling might maintain or even raise productivity. Where more organic matter reaches intermediate and deep waters, microbial respiration consumes oxygen, potentially lowering oxygen concentrations and expanding low oxygen zones. Such changes can further stress benthic organisms, particularly those sensitive to reduced oxygen availability. The sedimentary record hints at these conditions through the presence or absence of bioturbation, the mixing of sediments by burrowing animals. In intervals where oxygen is sufficient and benthic faunas are active burrows and mixed fabrics are common, during parts of the Paleocene-Eocene Thermal Maximum, some sites show reduced bioturbation or more laminated sediments, suggesting periods when benthic activity is diminished, possibly due to lower oxygen or to ecological disruption from acidification and warming. The response of other components of deep seafloor communities such as sponges, echinoderms, and various infaunal and epifaunal invertebrates is less well preserved in many deep ocean cores, but the trends observed in foraminifera indicate that the deep-sea biosphere does not remain unaffected. Circulation patterns in the deep ocean also evolve under the influence of surface warming and regional changes in density structure. The formation of deep waters in high-latitude regions depends on a balance between cooling evaporation and freshwater input from precipitation and runoff. During the Paleocene-Eocene Thermal Maximum, warmer surface temperatures and altered hydrological cycles can change the sites and properties of deep water formation. Some reconstructions and model studies suggest a shift in the dominance of different source regions, with implications for how oxygenated waters reach the depths, and how quickly chemical anomalies such as the increased dissolved inorganic carbon are ventilated. Deep waters formed in warmer climates carry higher temperatures and lower carbonate ion concentrations into the abyss, reinforcing the conditions that promote carbonate dissolution. The combined effect of altered deep water sources' widespread acidification and warming creates a deep ocean environment that is denser in carbon warmer and in places less hospitable to organisms that depend on stable, cool and carbonate-saturated conditions. Yet even in this transformed state, the deep ocean continues to act as a major sink for both heat and carbon, taking up a large fraction of the excess carbon dioxide released during the event and storing it on timescales of many thousands of years. As carbonate dissolves from sediments and neutralizes part of the added acidity, and as weathering on land slowly supplies new alkalinity to the sea, the chemical structure of the deep ocean begins to move toward a new balance. For the interval corresponding to the peak of the Paleocene-Eocene Thermal Maximum, however, the dominant features of the ocean interior remain clear: warmer, more acidic, deep waters, a shoaled carbonate compensation depth, widespread dissolution of carbonate sediments and stressed seafloor communities that together form the oceanic core of this hypothermal event. On the continents during the Paleocene-Eocene Thermal Maximum, the rapid warming of air and ocean does not only raise temperatures, it also strengthens the hydrological cycle and alters rainfall patterns in ways that change how rocks weather and how water moves through landscapes. Warmer sea surface temperatures increase evaporation over wide ocean areas, and the thicker, moisture-rich atmosphere carries more water vapor than in the late Paleocene background climate. As this enhanced vapor supply is drawn into circulation systems and lifted over coasts, mountain belts and interior plateaus, it condenses more readily and can deliver more intense or more frequent precipitation in many regions. Geological and geochemical records from soils, river deposits, and marginal basins indicate that parts of the planet experience stronger rainfall especially at high latitudes and in some low-latitude belts, where monsoon-like circulation patterns respond sensitively to the added heat. In these areas, storms move through air columns that start from higher temperatures and higher humidity, so when air rises and cools larger, amounts of water condense and fall as rain. Over high-latitude landmasses that border warm polar seas, this can produce long wet seasons with frequent rainfall and only brief cool intervals. In some mid-latitude and subtropical regions, the picture is more complex. The expansion or intensification of subtropical high-pressure zones and shifts in storm tracks can leave certain continental interiors drier on average, even as the global hydrological cycle as a whole becomes more vigorous. The rainfall may arrive in more concentrated bursts separated by longer dry spells, increasing the contrast between wet and dry periods and influencing how water infiltrates soils and how rivers respond to runoff events. Despite these regional differences, a broad signal of hydrological intensification emerges. More water vapor moves through the atmosphere, and when it falls as precipitation, it often does so in heavier events that have strong effects on weathering and erosion. Chemical weathering, the suite of reactions by which rocks at Earth's surface dissolve or transform under the action of water and dissolved substances, responds strongly to these changes in temperature and rainfall. In warm, wet conditions, rainwater that has absorbed carbon dioxide from the atmosphere and from soils forms weak carbonic acid, which reacts with silicate and carbonate minerals in bedrock and regolith. Higher temperatures accelerate many of these reactions, while increased rainfall raises the flux of water through soils and fractures, continuously bringing fresh reactants into contact with mineral surfaces and flushing reaction products away. During the Paleocene, Eocene Thermal Maximum, evidence from clay mineral soil profiles and dissolved load indicators suggests that silicate weathering rates rise in many regions, especially in humid belts where dense vegetation, thick soils and abundant moisture work together to break down primary minerals and form secondary clays. On slopes and uplands, these processes remove cations such as calcium, magnesium, sodium and potassium from rocks and transport them via groundwater and rivers toward the oceans, where they participate in the formation of carbonate minerals and help regulate ocean chemistry on timescales of tens of thousands of years. In low-lying areas, persistent weathering and leaching can strip soils of more soluble constituents, leaving behind accumulations of aluminium-rich clays that point to long periods of intense chemical alteration under warm, wet conditions. The strengthening of the hydrological cycle also affects physical weathering and erosion. Where rainfall events become more intense, large volumes of water can arrive in short periods, generating powerful surface runoff that scours hill slopes, cuts, channels, and mobilizes sediments ranging from fine silts to coarse gravels. On steep terrain, such downpours may trigger landslides and mass movements that rapidly remove weathered material and expose fresh rock surfaces, which then become sites for renewed chemical weathering. River systems respond by adjusting their channel patterns, floodplain extents and sediment loads to the new balance of water and sediment supply. In some basins, thicker packages of fluvial deposits accumulate that record episodes of frequent flooding and high sediment transport, while in others a shift toward more seasonal flow regimes imprints itself in alternations between channel sands and overbank fines. The interaction between chemical and physical weathering during the Paleocene-Eocene thermal maximum is therefore dynamic. Enhanced chemical alteration in warm wet regions weakens rock fabrics and generates thick regoliths, which are then more easily eroded during heavy rainfall events. The eroded material, once entrained in streams and rivers, continues to react with water and dissolved carbon, extending the weathering process downstream and into floodplains. Vegetation influences this interaction as well because plant roots, organic acids, and soil biota all participate in breaking down minerals and cycling nutrients. In regions where plant cover remains dense under the warmer climate, roots stabilize some slopes and soils, but they also maintain high rates of biological activity that support strong chemical weathering. Where vegetation structure changes in response to altered moisture regimes, such as in areas that experience more pronounced dry seasons, the balance between soil protection and exposure may shift, modulating how rainfall translates into erosion. The intensified rainfall and weathering have direct consequences for the global carbon cycle during the event. As silicate minerals weather, they consume carbon dioxide from the atmosphere, converting it into dissolved bicarbonate that rivers carry to the ocean. There, over long periods, this dissolved carbon can be locked into carbonate minerals that settle to the seafloor. In the context of the Paleocene-Eocene Thermal Maximum, this enhanced weathering acts as a negative feedback on the carbon perturbation, gradually drawing some of the added carbon dioxide out of the atmosphere-ocean system. However, the timescale on which this feedback operates is long compared with the rapid onset of warming, so during the peak of the event, the immediate impact of intensified weathering is more clearly expressed in the changing composition of soils, sediments, and river waters than in any quick reduction of atmospheric greenhouse forcing. Still, the chemical signatures of increased weathering, such as shifts in the relative abundances of certain elements and isotopes in marine and continental deposits, highlight the way continental surfaces respond when rainfall and temperature rise together. On land, these processes reshape the skin of the continents during the Paleocene-Eocene thermal maximum, thickening some weathering profiles, deepening others, and redistributing loose material across slopes, valleys, and floodplains, all under the influence of a strengthened hydrological cycle that is a direct expression of the event's extreme warmth. On land during the Paleocene-Eocene thermal maximum, the combination of higher temperatures and an invigorated hydrological cycle reshapes soils, river systems, and the pathways by which sediment moves from uplands to the sea. Soils which form at the interface between bedrock, atmosphere, water, and living organisms respond sensitively to changes in rainfall and heat. In many regions where precipitation becomes more abundant and more evenly distributed through the year, weathering fronts deepen and soil profiles thicken. Water percolating through these profiles carries dissolved carbon dioxide and organic acids produced by roots and microbes, and these fluids attack primary minerals in the parent material, transforming feldspars and mafic grains into fine-grained clays. Iron within the rock oxidizes and precipitates as coatings and nodules, producing reddish and yellowish hues, characteristic of strongly weathered, well-drained soils. Over time, repeated leaching removes more soluble ions such as calcium, sodium, and magnesium from upper horizons, leaving behind aluminium-rich clays and more resistant minerals. The resulting profiles record long periods of intense chemical weathering under warm, humid conditions, and in the sedimentary record they appear as paleosols with clear horizons, abundant clay root traces, and distinctive structures formed by shrink-swell cycles and biological activity. In other continental settings, especially where the changing circulation patterns create more pronounced wet and dry seasons, rather than uniformly wetter conditions, soils evolve differently. Their strong monsoon-like rainfall may saturate the ground during certain months, while extended dry intervals allow evaporation to exceed precipitation. In such climates, dissolved ions carried into the soil by infiltrating water can reprecipitate as carbonates or other salts when water is drawn back toward the surface and vapor is lost to the air. The result is the development of soils with carbonate nodules, calcareous horizons, or even more extensive carbonate accumulations marking zones where water flow slows and solutes accumulate. At depth, these features preserve information about the balance between leaching and evapotranspiration, and about the seasonality of moisture supply during the Paleocene-Eocene thermal maximum. In high-latitude regions around warm polar sea soils that previously formed under cool but mild conditions, now experience longer growing seasons, deeper thawing, and more vigorous biological cycling. Thick organic rich horizons develop where plant productivity is high, and decomposition keeps pace but does not entirely remove accumulating litter. In some low-lying areas, poor drainage and frequent rainfall create waterlogged conditions that lead to glade soils with mottled colours and iron reduction features. These contrasting soil types, from deeply weathered upland profiles to seasonally saturated lowland soils together, document the range of hydrological responses on land under extreme greenhouse warmth. River systems integrate these changes across catchments and carry the products of weathering and erosion toward basins. With more intense or more frequent rainfall in many regions, discharge regimes become more variable, and high-flow events capable of mobilizing large quantities of sediment occur more often. On steep slopes and in mountainous terrain, heavy rains trigger rapid overland flow and debris movement. Weathered mantles loosened by chemical alteration and root activity can fail in shallow landslides, delivering pulses of material into headwater channels. These channels enlarge and adjust their cross-sections to accommodate higher peak flows, and they convey gravel, sand, and finer particles downstream. As rivers emerge from confined valleys onto broader plains, their response depends on discharge variability, sediment supply, and the gradients available under high sea levels. In some basins, the combination of abundant coarse material and fluctuating flows favors braided river patterns with multiple shifting channels separated by bars that are frequently reworked. These systems build thick packages of cross-bedded sands and gravels, punctuated by overbank fines deposited during floods that spill beyond the main channels. In other settings where gradients are low and vegetation helps stabilize banks meandering rivers dominate. Their sinuous channels migrate slowly across floodplains, eroding on outer bends and depositing point bar sediments on inner bends. During high water stages, these rivers overflow their banks and lay down sheets of silt and clay over wide areas, gradually constructing broad, flat floodplains mantled by fine-grained alluvium. Within these floodplain deposits, periods of relative stability allow soils to form only to be buried by subsequent overbank events. The stacking of such paleosols and flood layers in sedimentary sequences from the Paleocene-Eocene thermal maximum provides a detailed record of how often rivers overtopped their banks, how quickly floodplains are graded, and how the balance between stability and disturbance evolved under the influence of intensified hydrology. In interior basins and low-relief regions, rivers fed by strengthened rainfall and more active weathering may develop expansive alluvial plains and interconnected networks of channels and lakes. Ephemeral lakes and wetlands form in topographic depressions, filling during wet periods and shrinking or drying during dry phases. Their sediments, composed of laminated muds, evaporate minerals or organic rich layers, depending on local water balance, capture changes in the timing and magnitude of inflow, evaporation, and groundwater exchange. Where standing water persists for long intervals, fine-grained sediments settle quietly while shorelines migrate, in response to water level changes driven by climate and by slow tectonic adjustments. Marginal to major river systems, smaller tributaries and fans convey material from uplands to main valleys. Alluvial fans, which form where confined flows emerge onto open slopes, respond quickly to shifts in storm frequency and intensity. During episodes of enhanced high-intensity rainfall, they may prograde, building out thick, coarse, wedge-shaped bodies of conglomerate and sandstone through repeated deposition of debris flows and hyper-concentrated floods. During quieter intervals, soils and vegetation can stabilize fan surfaces, creating a patchwork of active and inactive lobes that together record the pulse nature of sediment delivery. The transfer of sediment from continents to the oceans is also modulated by the position of shorelines under high sea level conditions. Because the absence of large ice sheets and the thermal expansion of warmed water already hold sea level high, coastal plains are broad and gradients gentle. Rivers often approach the sea through low-angle profiles, depositing part of their load well inland as they lose energy, while suspended fine material continues toward estuaries and deltas. In some settings, strengthened discharge and sediment supply allow deltas to advance into shallow epicontinental seas, constructing lobes of sand and silt that prograde over older marine deposits. In others, coastal accommodation space created by tectonic subsidence or by the shape of basins allows thick accumulations of mud, sand, and organic matter to build up without the shoreline moving far seaward. These coastal and deltic accumulations act as key archives of sediment transfer during the Paleocene-Eocene Thermal Maximum, preserving evidence of changing river behavior, sediment loads, and relative sea level. As sediments move along these pathways, they carry not only mineral grains, but also organic matter and adsorbed nutrients. Plant debris from floodplains, soils and upland forests enters channels during storms, floats or sinks depending on its properties, and may be decomposed along the way or buried in floodplain and deltic deposits. Fine particles with organic coatings can travel longer distances, delivering terrestrial carbon to estuaries and continental shelves. Under certain conditions, such as in stratified estuaries or restricted embayments, this organic matter can contribute to the formation of organic-rich layers that later form part of the geological record. The balance between oxidation and burial of this material influences how much continental organic carbon becomes part of longer-term sedimentary reservoirs. Though on the timescale of the Paleocene-Eocene Thermal Maximum peak, the immediate visible impact lies in the architecture and composition of sediment bodies. Geochemical traces within these soils and sediments, including elemental ratios and isotopic signatures, give additional insight into the intensity of weathering and the sources of material. Shifts in the proportions of certain clay minerals track the degree of leaching and the temperature and moisture conditions under which they form. Variations in the ratios of weathering resistant to easily altered elements indicate how thoroughly rocks have been broken down. Together with sedimentological observations of grain-size structures and stacking patterns, these signals show that during the Paleocene-Eocene Thermal Maximum, continental surfaces are not static backdrops to climate change but active evolving systems. Soils deepen or reorganize, rivers shift their channels, and floodplains and sediment is reworked and redistributed across landscapes and into basins as part of a strengthened climate-driven coupling between the atmosphere, hydrosphere, and lithosphere. During the Paleocene-Eocene Thermal Maximum, land ecosystems adjust to the combined influence of higher temperatures, altered rainfall patterns, and changing soils, and these adjustments play out through shifts in vegetation structure, plant ranges, and the distribution and body size of mammals. Forests that already cover much of the low and mid-latitude continents in the late Paleocene experience further expansion and rearrangement as warmth intensifies. In tropical belts, evergreen broadleaf forests remain widespread, but their composition shifts toward lineages that tolerate or prefer even warmer conditions, and in many areas higher rainfall. Canopies are dense, multi-layered and continuously productive, with rapid leaf turnover and active nutrient cycling in thick, moist litter layers. Understory plants compete for filtered light, and vines and lianas climb trunks toward the sunlit upper levels. The warmth of the Paleocene-Eocene thermal maximum stretches these tropical and subtropical-like conditions poleward. In mid-latitude regions that previously host mixed forests, with a blend of temperate and subtropical elements, new plant taxa that favour warmer climates appear and spread. Leaf assemblages preserved from these zones often show a higher proportion of large, smooth-edged leaves, consistent with higher mean annual temperatures and in some areas increased humidity. Deciduous habits persist in places where seasonal cycles in light and moisture still favour leaf drop, but evergreen forms become more prominent where winters are milder and frost is rare. At high latitudes where late Paleocene climates are already mild enough to support forests, the Paleocene-Eocene thermal maximum brings further warming and a reshaping of plant communities. Coastal lowlands near warm polar seas support forests with diverse combinations of conifers and broadleaf trees, including species that in later cooler times will be confined to much lower latitudes. These high-latitude forests grow through long summers with extended daylight and endure winters that, although dark, are no longer very cold. Tree rings, leaf fossils, and associated pollen records indicate vigorous growth and a strong seasonal rhythm under these conditions. Wetlands occupy depressions and poorly drained areas, forming peat, forming mires, swamp forests and back-swamp environments along sluggish river reaches. The intensification of the hydrological cycle during the event means that many of these high and mid-latitude regions experience frequent or persistent rainfall, sustaining saturated soils and dense vegetation. In contrast, some continental interiors closer to subtropical high-pressure belts see a different pattern with more pronounced alternations between wet and dry periods. Their open woodland, shrublands, or forest savanna mosaics may expand at the expense of closed canopy forests, especially on well-drained uplands. Plants adapted to seasonal water stress with deeper roots or drought-tolerant leaves gain footholds in these landscapes. The changing climate also affects plant phenology, the timing of growth flowering and seed production. Longer growing seasons in many regions allow multiple flushes of leaves or extended periods of active growth, while altered rainfall patterns shift the onset and duration of peak productivity. These adjustments influence not only the plants themselves but also the animals that depend on them for food and habitat. One of the striking aspects of terrestrial life during the Paleocene-Eocene thermal maximum is the response of mammals, which already are diversifying during the Paleocene and now experience both range expansions and changes in body size. Warmer conditions and the presence of land connections at high northern latitudes between some continental masses create corridors that mammals can use to move between regions that are now separated by wide oceans. Forested routes across areas that will later be more inhospitable allow early primates, hoofed mammals and other groups to disperse between North America and Eurasia, and possibly between Eurasia and other landmasses. Fossil assemblages show that mammal faunas on different continents become more similar to one another during and just after the event, indicating that lineages have crossed previous barriers and established themselves in new ranges. Alongside these dispersals, many mammal lineages display a tendency toward reduced body size during the event. In several early horse-like artiodactyl and primate groups, skeletal remains from the Paleocene-Eocene thermal maximum are smaller than those from immediately before and after. This dwarfing pattern occurs over the timescale of the event, and then reverses as conditions begin to cool in the recovery phase. The exact mechanisms driving these changes are still under investigation, but they likely involve a combination of factors related to temperature, resource availability, and life history. Smaller body size can influence heat exchange with the environment and metabolic demands, and it also reflects the nutritional environment in which juveniles grow. Under warmer climates, with possible changes in plant quality, or in the seasonality of food supply selection or developmental constraints, may favour smaller adult sizes for some taxa during the peak of the event. Vegetation structure and mammal ecology are closely linked. In densely forested regions, arboreal and scansorial mammals exploit the three-dimensional habitat provided by trunks, branches, and lianas. Early primates which appear and diversify around the time of the Paleocene-Eocene boundary make use of these forest canopies, feeding on fruits, leaves, and insects. Their dispersal across connected forest belts during the Paleocene-Eocene Thermal Maximum is aided by the continuity of wooded environments at high latitudes. On the forest floor and in more open habitats, ungulate-like mammals browse on leaves, shoots, and possibly fruits, while smaller omnivores and insectivores move through the leaf litter and undergrowth. Insects respond strongly to the warmer and often wetter conditions as well, and their interactions with plants leave visible traces. Fossil leaves from this interval frequently show a high diversity and intensity of damage types, including chewing, mining, galling, and piercing, suggesting that herbivorous insects are abundant and ecologically varied. These feeding activities can influence plant community composition by preferentially targeting some species or tissues, and they contribute to the cycling of nutrients through rapid breakdown of leaf material. Pollinating insects also participate in the reproduction of many flowering plants, forming part of a web of mutual dependencies that are sustained under the new climatic regime. Fire regimes, which depend on the interplay between fuel availability, moisture, and ignition sources, may also adjust under Paleocene-Eocene thermal maximum conditions. In some regions, increased rainfall and high humidity reduce the likelihood of large frequent fires, allowing closed canopy forests to remain dominant. In others, where seasonal drying persists or intensifies, episodes of fire can open canopies, favour fire-adapted species, and help maintain more open woodland or savanna-like landscapes. Charcoal layers and other fire indicators in sediments provide clues to these patterns, though the global picture remains patchy. Across all these environments, terrestrial ecosystems remain productive and dynamic under the extreme warmth of the event. Plants, insects, and vertebrates persist and adapt through range shifts, changes in abundance, and morphological adjustments. Some lineages expand their distributions and diversify, taking advantage of newly accessible habitats and corridors, while others experience stresses that lead to local or regional declines. The overall structure of many ecosystems, with forests in humid zones, more open biomes in seasonally dry areas, and wetlands in low-lying regions, persists. But the details of species composition, interactions, and spatial extent shift in response to the altered climate. From the perspective of the Paleocene-Eocene thermal maximum narrative, this layer of land response is characterized by poleward migration of warm adapted vegetation, reorganization of forests and open habitats under intensified hydrology, and active mammal dispersal and dwarfing, all unfolding on land surfaces whose soils, rivers, and relief are themselves being reshaped by the same warming that drives ecological change. In the oceans during the Paleocene-Eocene thermal maximum, the communities of plankton that drift in sunlit surface waters and the organisms that live on and within the seafloor respond in complex ways to the combined stresses of warming acidification and altered nutrient dynamics. At the surface, phytoplankton continue to capture sunlight and fixed carbon forming the base of marine food webs, but their composition and distribution adjust to the new conditions. Calcareous nanoplankton, which build tiny plates of calcium carbonate, remain important in many regions, yet the patterns of species dominance shift with some taxa that tolerate warmer, more stratified waters, becoming more abundant while others decline. In certain basins, blooms of particular dinoflagellate cyst producers, including forms that favor warm nutrient-rich surface layers, leave dense accumulations of resistant organic microfossils in sediments marking intervals when the surface ocean supports high primary productivity or experiences episodes of ecological imbalance. The strong stratification that develops in many parts of the ocean during the Paleocene-Eocene Thermal Maximum plays a central role in shaping plankton communities. In low and mid-latitude regions, a warm, buoyant surface layer rests more stably above cooler, denser waters, reducing the vertical mixing that normally supplies nutrients from depth to the sunlit zone. Where this reduced mixing is not offset by upwelling or riverine inputs, nutrient limitation can develop in surface waters, favoring phytoplankton groups that thrive under low nutrient conditions and can efficiently recycle nitrogen and phosphorus within the upper ocean. In contrast, in coastal upwelling zones and along some continental margins, winds and currents still drive the ascent of deeper nutrient-rich water, supporting productive assemblages that differ from those in the more strongly stratified open ocean gyres. The result is a mosaic of plankton communities whose structure reflects local balances between stratification upwelling and nutrient regeneration. Zooplankton, including planktonic foraminifera that construct calcium carbonate shells, graze on these primary producers and on smaller heterotrophs. These shells of planktonic foraminifera preserve both the isotopic and elemental signatures of the waters in which they grow, recording the warming and carbon cycle perturbation of the event. But the assemblages themselves also change. Some species that are adapted to cooler or more weakly stratified conditions decline in abundance or disappear from certain regions, while others that tolerate higher temperatures and perhaps lower carbonate saturation states become more common. In some sections, the diversity of planktonic foraminifera decreases during the peak of the Paleocene-Eocene Thermal Maximum, and then recovers gradually afterward, indicating that surface-dwelling calcifiers do not escape ecological pressure, even though their extinction patterns are less severe than those of their deep-sea counterparts. The altered balance between carbonate production and dissolution, associated with ocean acidification, also influences plankton communities. As carbonate ion concentrations in surface waters fall somewhat due to the increased dissolved carbon, the energetic cost of calcification may rise for organisms that build shells or skeletons of calcium carbonate. This effect is moderated by the large buffering capacity of the upper ocean and by the continuing supply of alkalinity from rivers, yet in combination with warming and potential shifts in food webs, it may contribute to changes in the relative success of different calcifying groups. Some calcareous nanoplankton species show reduced size or changes in plate morphology during the event features that may reflect environmental stress. Siliceous plankton such as diatoms and radiolarians also respond to the evolving conditions. In nutrient-rich high-latitude and some upwelling-influenced regions, diatoms continue to play a prominent role in primary production, using dissolved silica to build their frustules. Changes in silica supply driven by weathering on land and by circulation in the ocean can alter their abundance and the species that dominate. Radiolarians, which construct silica skeletons and occupy a range of depths in the water column, likewise adjust their distributions. In some deep-sea sections, radiolarian faunas show shifts in composition across the Paleocene-Eocene Thermal Maximum interval, likely tied to changes in surface productivity thermocline structure, and water mass properties. As plankton live, grow and die in these altered oceans, they continue to export organic carbon and biogenic minerals to the interior. Particles sink through the water column as aggregates, fecal pellets and individual shells, feeding heterotrophic organisms at depth and delivering material to the seafloor. Under the warmer, more stratified conditions of the event, the efficiency with which this biological pump transports carbon may change regionally. In some areas, reduced nutrient supply to the surface could lower export flux, while in others, periods of high productivity driven by upwelling or by episodic nutrient injections might enhance sinking fluxes. The respiration of sinking organic matter in subsurface layers consumes oxygen and releases dissolved inorganic carbon, reinforcing the chemical changes associated with the event. At the seafloor, communities of benthic organisms face the combined challenges of warmer bottom waters, reduced carbonate saturation, and in some locations lower oxygen concentrations. The benthic foraminiferal extinction that coincides with the onset of the Paleocene-Eocene Thermal Maximum represents one of the most notable biological signals of the event in the deep ocean. A substantial fraction of species that inhabit abyssal and bathyal sediments in the late Paleocene vanish from the record within a relatively short interval, replaced by opportunistic forms that can tolerate the new environmental conditions. The survivors often include small, thin-walled species and those with life strategies suited to variable or stressed habitats. Above the deep sea on continental slopes and shelves, benthic communities respond in more diverse ways. In some settings where oxygen remains sufficient and carbonate saturation does not fall as low, a broader range of foraminiferal taxa persists and extinction intensity is lower. Macrofaunal invertebrates such as mollusks, echinoderms and annelids continue to inhabit the sediment-water interface, bioturbating the upper layers of mud and sand. Their burrowing activities where present mix organic matter and oxygen into the substrate-sustaining redox gradients that support complex microbial communities. In other shelf and upper slope regions, however, the combination of higher organic matter flux and reduced ventilation can produce intervals of lower oxygen. Their benthic faunas may contract and sediment fabrics reflect reduced bioturbation, with more laminated structures and fewer burrows. The degree to which these conditions develop varies from basin to basin, influenced by local productivity circulation and basin geometry. Microbial life in sediments and at the seafloor-water interface continues to play a crucial role in processing organic matter and mediating chemical cycles during the Paleocene-Eocene Thermal Maximum. As organic particles arrive at the sediment surface, bacteria and archaea break them down, releasing dissolved inorganic carbon nutrients and reduced compounds such as ammonium and hydrogen sulfide. These byproducts fuel further microbial processes, including nitrification, denitrification, and sulfur oxidation, which in turn influence the chemistry of pore waters and overlying bottom waters. Under more acidic conditions, dissolution of carbonate shells and matrix within sediments adds another dimension to this microbially active environment, as carbonate minerals provide buffering against pH changes and release calcium and carbonate ions that help restore saturation states over time. On continental shelves where light can reach the seabed in shallow areas, benthic primary producers such as seagrasses and some algae may expand or contract depending on water clarity, temperature, and nutrient availability. Warm, shallow seas with stable, clear waters can support extensive meadows and algal mats that stabilize sediment, cycle nutrients, and provide habitat for invertebrates and fishes. Where increased runoff from land delivers higher loads of fine sediment and nutrients, water turbidity may rise, limiting light penetration and shifting communities toward those tolerant of lower light and more variable conditions. In carbonate platforms and reef environments, calcifying organisms such as corals, calcareous algae, and various invertebrates react to the combined influences of warming and acidification. High temperatures can stress some reef-building corals, while lower carbonate saturation states can make calcification more demanding. Yet the geological record of shallow water, carbonates across the Paleocene-Eocene Thermal Maximum, is not uniform, and many platforms continue to produce carbonate sediments, though often with changes in community composition and skeletal assemblages. The balance between coral-dominated frameworks, algal buildups, and non-skeletal carbonate precipitation shifts in ways that depend on local conditions, water depth, and the duration and severity of stress. Throughout the water column and at the seafloor, these biological responses unfold over the duration of the event, which spans many tens of thousands to a few hundreds of thousands of years from onset through recovery. Plankton and benthos alike adjust through compositional turnover changes in abundance, and in some cases morphological shifts, while the overall functioning of marine ecosystems persists. Primary production continues, consumers still graze and prey, and detritus still sinks to nourish the deep biosphere. The stress imposed by rapid warming and acidification is evident in extinctions and reorganizations, especially in the deep sea, but the marine biosphere does not collapse. Instead, it reconfigures itself within the constraints imposed by the altered physical and chemical environment, leaving in the fossil record a detailed layered account of how ocean life responds when the climate system moves abruptly into a more extreme greenhouse state. The large negative carbon isotope excursion that defines the Paleocene-Eocene Thermal Maximum points to a substantial injection of carbon with a light isotopic signature into the combined ocean-atmosphere reservoir, and the search for the sources, triggers, and feedbacks of this carbon release focuses on several plausible contributors whose relative importance remains under active study. The magnitude of the excursion, together with modelling of ocean acidification and carbonate dissolution, indicates that the total added carbon is on the order of many thousands of petagrams introduced over a geologically short interval of at most several tens of thousands of years, and probably less. Such a perturbation requires reservoirs that already hold large amounts of isotopically light carbon, and mechanisms capable of releasing it quickly once conditions cross certain thresholds. One candidate source lies in magmatic activity associated with the North Atlantic igneous province, which is active around the time of the event. As this province develops, sheets and bodies of magma intrude into thick sequences of organic rich sedimentary rocks along rifted continental margins. The thermal metamorphism of these sediments as they are heated by the intruding magma can generate large volumes of carbon dioxide and methane with isotopic compositions that are significantly lighter than the pre-event ocean atmosphere carbon pool. Fractures vents and hydrothermal systems associated with the igneous activity provide pathways for these gases to reach the surface and enter the atmosphere and ocean. Geological evidence for such processes includes widespread volcanic and intrusive rocks in the region, structures that resemble vent complexes in seismic data, and geochemical signatures of thermogenic gas generation preserved in some sedimentary units. These observations support a role for magmatic degassing and thermogenic carbon release as important components of the Paleocene-Eocene Thermal Maximum carbon budget, though the exact quantity and timing of these emissions remain constrained within ranges rather than fixed values. Another often discussed reservoir is methane stored in marine sediments, as gas hydrates crystalline compounds in which methane molecules are trapped within cages of water ice, under conditions of low temperature and high pressure. In a warm greenhouse climate, such hydrates would preferentially occur in sediments along continental margins at intermediate depths where temperatures are cool enough and pressures high enough to stabilize them. Warming of bottom waters and of sediments during the Paleocene-Eocene Thermal Maximum could move parts of this hydrate inventory outside its stability field, leading to dissociation of hydrate and release of methane into pore waters and ultimately the overlying ocean. Once in the water column and atmosphere, most methane would oxidize to carbon dioxide on timescales much shorter than the duration of the event, preserving its light isotopic signature while altering the greenhouse balance. The shape and size of the carbon isotope excursion, together with calculations of how much methane hydrate might plausibly be stored in sediments before the event, are used to evaluate the potential contribution of hydrates. While some scenarios show that hydrate release alone may not provide the entire required mass of carbon, many studies consider it a likely amplifying feedback that responds to initial warming from other sources by adding further light carbon to the system. A related set of processes involves oxidation of organic carbon stored in soils, peats, and sedimentary rocks on land and in shallow marine environments. Under the warmer conditions of the Paleocene-Eocene Thermal Maximum, soil respiration and decomposition rates increase in many regions, releasing more carbon dioxide from continental organic reservoirs. Drying of some wetlands, changes in water tables, and episodes of fire can expose previously buried organic matter to oxygen, leading to its combustion or decay and further carbon release. On some continental margins, tectonic uplift or erosion may strip away overburden from organic-rich strata, enhancing their exposure and oxidation. Organic carbon in these reservoirs carries a strongly light isotopic signature, so its transfer to the atmosphere and ocean contributes to the observed excursion. The magnitude of this contribution is difficult to quantify precisely because the size and accessibility of pre-event terrestrial carbon stocks and the degree of their mobilization during the event are not fully known. Nonetheless, isotopic and elemental data from soils, coals, and shallow marine deposits suggest that oxidation of organic carbon on land and along margins is part of the broader carbon release story. Volcanic degassing in general, beyond the specific case of thermogenic processes in sedimentary basins, also remains a fundamental source of carbon. Mid-ocean ridges, arc volcanoes, and intraplate magmatic centers continuously emit carbon dioxide from Earth's interior, and changes in the rate or style of this activity can alter the long-term carbon input. For the Paleocene-Eocene Thermal Maximum, the coincidence in time between the event and phases of enhanced magmatism in the North Atlantic region hints that variations in volcanic flux may have provided part of the initial forcing that pushed the system toward rapid warming and set up conditions for additional feedbacks to operate. However, the isotopic composition of mantle-derived carbon is not as light as that of organic reservoirs, so even if volcanic emissions play a major role in raising carbon dioxide levels, the extreme lightness of the carbon isotope excursion still requires substantial input from organic or methane-like sources. The temporal structure of the event, as recorded in some high-resolution sedimentary sections, offers clues to the sequence of triggers and feedbacks. In certain records, the carbon isotope excursion appears to unfold in one main step, followed by smaller pulses or modulations, while in others the onset can be resolved into several phases. These patterns are consistent with scenarios in which an initial carbon input, perhaps dominated by magmatic or thermogenic emissions, rapidly warms the climate and begins the isotope shift, and this warming then destabilizes additional reservoirs such as methane hydrates and terrestrial organic carbon, adding further light carbon in a series of feedback responses. The relative contributions and exact timing of these steps differ among reconstructions, and no single sequence has universal support. But the idea that multiple sources and feedbacks combine to produce the full excursion is widely considered. Against this framework of carbon release, several feedbacks start to operate that tend to counteract the perturbation, though they do so on longer timescales than the initial input. One of the most important negative feedbacks is the enhancement of silicate weathering on land under warmer and often wetter conditions. As described earlier, chemical weathering consumes atmospheric carbon dioxide and delivers dissolved bicarbonate and cations to the ocean, where they eventually form carbonate minerals. During the Paleocene-Eocene Thermal Maximum, intensified weathering in many regions increases this flux, gradually removing some of the added carbon from the atmosphere-ocean system. However, the timescale on which this process significantly reduces carbon dioxide concentrations is on the order of many tens to hundreds of thousands of years, much longer than the rapid onset of the event, so its primary role lies in influencing the trajectory of the later phases rather than in limiting the initial warming. Another important buffering mechanism operates within the ocean through carbonate dissolution and subsequent reprecipitation. As the added carbon drives acidification and shoals the carbonate compensation depth seafloor, carbonate dissolves, releasing carbonate ions that help neutralize the excess dissolved carbon. Over time, this dissolution and the later burial of new carbonate formed from weathering-derived ions act to restore the balance between the alkaline and carbon components of seawater. This feedback is more rapid than silicate weathering acting, over many thousands to perhaps tens of thousands of years, and it largely governs the evolution of deep ocean chemistry and carbonate preservation during and after the event. In some settings, enhanced burial of organic carbon may also function as a modest negative feedback. If warmer stratified conditions lead to greater accumulation of organic matter in certain anoxic basins, whether in marine settings or in continental lakes and wetlands, the net effect is to sequester some carbon away from the active short-term cycle. The evidence for substantial global increases in organic burial during the Paleocene-Eocene Thermal Maximum is mixed, with some regions showing organic-rich intervals and others not. So this pathway is likely a secondary contributor compared with weathering and carbonate dissolution. Alongside these negative feedbacks, there are also positive feedbacks that can amplify warming once it begins. The potential destabilization of methane hydrates is one such mechanism, as initial warming of bottom waters can release methane that further strengthens greenhouse forcing after oxidation. Increased respiration of soil and peat carbon under higher temperatures likewise adds carbon dioxide to the atmosphere, reinforcing the perturbation created by other sources. Changes in vegetation cover, such as shifts from high albedo snow-covered landscapes to darker forested surfaces at high latitudes, can reduce reflectivity and enhance local warming, indirectly supporting the persistence of high temperatures. These positive feedbacks operate on a range of timescales, from relatively rapid responses in soil respiration and hydrate stability to slower adjustments in vegetation and surface properties. The interplay between trigger sources and feedbacks during the Paleocene-Eocene Thermal Maximum thus involves a sequence in which one or more primary drivers introduce a large quantity of light carbon into the atmosphere, and ocean rapid warming and ocean acidification follow, and then a suite of slower acting geochemical and climatic processes begins to draw the system gradually back toward a new balance, while some feedbacks continue to release additional carbon. The precise partitioning of the total carbon input among volcanism, thermogenic release hydrates and terrestrial organic reservoirs, as well as the detailed chronology of pulses, remains incompletely constrained, and different lines of evidence emphasize different aspects of the problem. What emerges clearly, however, is that the event reflects both a substantial external or tectonic forcing and a strong internal coupling between climate and the carbon cycle, with positive and negative feedbacks woven through the evolution of the hyperthermal episode. After the abrupt onset and the peak warmth of the Paleocene-Eocene Thermal Maximum, the climate and carbon system begin a gradual movement toward cooler, more stable conditions, a process that unfolds over many tens to hundreds of thousands of years and leaves a lasting mark in sediments and geochemical records. The large addition of light carbon that drove the initial isotope excursion does not continue indefinitely. Once the main sources of carbon release, whether magmatic, thermogenic, hydrate-based, or from organic reservoirs, diminish or cease the rates at which carbon enters the atmosphere, and ocean from these sources fall back toward the background levels governed by volcanism and long-term tectonics. At that point, the carbon cycle is left with an expanded ocean atmosphere reservoir, carrying an isotopic and chemical imprint of the event, and its subsequent evolution is controlled by processes that remove or redistribute carbon on longer timescales. One of the most important of these processes is the continued silicate weathering of continental rocks under the warm, often wet conditions that characterize much of the event and the early phases of recovery. As rainwater laden with carbon dioxide and organic acids reacts with silicate minerals, it consumes atmospheric carbon dioxide and generates dissolved ions and bicarbonate that rivers deliver to the oceans. There, these solutes contribute to the formation of carbonate minerals that eventually settle to the seafloor. Over many tens to hundreds of thousands of years, this enhanced weathering gradually draws down part of the excess carbon from the combined atmosphere and surface ocean, shifting the balance of the carbon cycle back toward a state where inputs and outputs match at lower carbon dioxide levels than at the event peak. The rate at which this drawdown proceeds is constrained by the availability of fresh rock surfaces, the intensity of rainfall, and the capacity of rivers and ocean basins to transport and store the products of weathering, so it is not instantaneous, but instead forms a long, declining tail in the climate response. Within the ocean, buffering processes associated with carbonate chemistry work alongside weathering to restore a new balance. During the early and peak phases of the Paleocene-Eocene Thermal Maximum, deep waters become more acidic, and the carbonate compensation depth shoals causing widespread dissolution of carbonate sediments on the seafloor. This dissolution neutralizes some of the added dissolved carbon and releases carbonate ions back into seawater, gradually increasing the saturation state of calcium carbonate in the deep ocean. As weathering continues to supply additional alkalinity from land, conditions slowly shift from net dissolution back toward net precipitation and burial of carbonate. In sedimentary records, this evolution is visible as an interval in which clay-rich or carbonate-poor layers that formed during the peak of acidification are overlain by renewed carbonate accumulations, sometimes with an overshoot in carbonate content relative to pre-event levels, as the system temporarily favors carbonate preservation and burial. The carbon isotope record also traces the recovery. After the sharp negative excursion at the onset, values begin to climb back toward heavier, more positive compositions as the influence of the added light carbon diminishes and as new carbon from volcanic and weathering-related sources, which is relatively heavier, mixes into the ocean atmosphere pool. This return does not simply reverse the excursion in a mirror image. Instead, it typically appears as a more gradual, sometimes asymmetrical path that reflects the combined effects of decreasing light carbon inputs, ongoing internal recycling, and the slow external removal of carbon through weathering and burial. In some sections, the isotope curve shows smaller superimposed fluctuations that may represent shorter-term variations in carbon cycling or additional modest pulses of carbon release. But the dominant trend is a steady rise from minimum values toward a new baseline that is closer to, though not necessarily identical with pre-event conditions. Temperature proxies in both marine and terrestrial archives register a similar tapering of warmth. Oxygen isotope ratios and other indicators of water temperature in marine shells show that surface and deep ocean temperatures, after reaching maxima during the peak of the Paleocene-Eocene Thermal Maximum, begin to decline. The drop is not immediate but occurs over extended intervals consistent with the large heat capacity of the oceans and the slow pace at which heat is lost to space once greenhouse forcing is reduced. On land leaf physiognomy, soil carbonate markers and other climate-sensitive indicators likewise document a move toward cooler conditions, with mean annual temperatures falling from their peak values and seasonal cycles adjusting accordingly. High latitude regions which had experienced some of the strongest warming and hosted forests, under very mild conditions, gradually cool, though not necessarily returning to pre-event climates in a simple way. As temperatures fall and carbon dioxide declines, vegetation belts adjust again. Some plant taxa that had expanded poleward during the event retreat toward lower latitudes, while others adapted to slightly cooler or more seasonal environments, reoccupy regions they had previously ceded. In mid and low latitudes, shifts in rainfall patterns and in the intensity of the hydrological cycle accompany the temperature changes, altering the balance between evergreen and deciduous forests, open woodlands, and other biomes. The dwarfing observed in some mammal lineages during the peak of the event reverses in many regions, with body sizes increasing again as climates cool and as the ecological and nutritional environments change. Dispersal pathways that had been opened along warm high-latitude corridors may become less favorable, as conditions there become more seasonal or cooler. But the faunal exchanges that took place during the event leave a lasting biogeographic legacy, with lineages now established on multiple continents continuing to evolve in their new ranges. In the deep ocean benthic foraminiferal communities, which had suffered significant extinction at the onset of the Paleocene-Eocene Thermal Maximum, begin to rebuild in the post-event interval. New species appear, some descended from surviving lineages, and others representing immigrants from different depth or regional habitats. The diversity and composition of these assemblages gradually approach those of more typical early Eocene deep-sea faunas, but the precise mix of species differs from that of the late Paleocene, reflecting both the extinctions and the altered environmental conditions of the recovering ocean. Carbonate preservation improves as bottom waters become less acidic, and as the carbonate compensation depth deepens again, allowing more shells to survive in sediments and enhancing the fossil record of these recovering communities. Planktonic communities also adjust, with some species that had prospered during peak warmth declining as temperatures moderate and stratification patterns change, while others better suited to the evolving conditions increase in abundance. River systems and soils record the recovery in their own ways. As climates cool, and in some regions as the strength and seasonality of rainfall change, weathering profiles stabilize or evolve toward forms more typical of early Eocene backgrounds. In some humid areas, the deep, intensely leached soils, formed under the combined influence of high temperature and strong rainfall, persist as long-lived features, while in others changes in drainage or vegetation lead to truncation or burial by younger sediments. River deposits record shifts in discharge regimes and sediment loads, with some systems transitioning back from highly variable flash flood-dominated patterns toward more stable flow regimes as extreme rainfall events become less frequent or less intense. Coastal and shallow marine environments continue to accumulate the products of continental erosion and marine productivity, building stratigraphic successions in which the layers corresponding to the Paleocene-Eocene thermal maximum form a distinct package often bounded below by late Paleocene deposits and above by early Eocene strata that reflect the recovered state of the climate and carbon cycle. In many parts of the world, this package is readily recognizable by its combination of lithological fossil and geochemical features. Clay-rich horizons marking episodes of deep ocean carbonate dissolution, negative carbon isotope excursions, followed by gradual recovery shifts in microfossil assemblages, and evidence of ecological change on land and in the sea, all cluster within a relatively narrow slice of geological time. Because of this distinctiveness and global extent, the Paleocene-Eocene thermal maximum serves as a useful marker horizon in stratigraphy, allowing correlation between widely separated sections and providing a reference point for studying early Cenozoic climate dynamics. The long-term legacy of the event extends beyond its role as a marker. By perturbing the carbon cycle and climate system so strongly, the Paleocene-Eocene thermal maximum leaves behind an ocean whose carbonate system has been reset through extensive dissolution and reprecipitation, a biosphere that has experienced pulses of extinction, dispersal, and evolutionary innovation, and continental surfaces that have been reshaped by intensified weathering and erosion. In the millions of years that follow, Earth's climate continues to evolve under the combined influence of changing greenhouse gas levels, tectonic rearrangements, and orbital forcing, but the sediments and fossils laid down during and after the event preserve a detailed record of how the system responded to a major rapid carbon release. This geological memory, written in stacked layers of mud sands, carbonates, and organic rich beds in the isotopic compositions of carbon and oxygen, and in the changed distributions of plant and animal lineages, is what remains of the Paleocene-Eocene thermal maximum, long after temperatures have cooled, and the carbon that once drove extreme warmth has been transferred into more stable reservoirs deep within rocks and sediments.